Hello and welcome to STAT 441 at Virginia Commonwealth University. In this lecture, we will learn about one of the discrete distributions, which is called the binomial distribution. To understand the binomial distribution, we will first need to understand what a Bernoulli trial is. So what we will see is that a lot of discrete distributions to the first basis of the experiment or the process is that it is a sequence of trials which are called the Bernoulli trials. Bernoulli trial is a very simple experiment, just like tossing a coin, where there are only two possible outcomes. So when you toss the coin, there are two possible outcomes. You can get heads or tails. Okay. So any experiment which has only two possible outcomes, which are mutually exclusive of each other, would be a Bernoulli trial. And we can define the outcomes as a success and a failure. So let's say tossing a coin, there are two outcomes that occur, heads or tails. We can define getting heads as our success, and therefore getting tails will be the failure. Okay, think of another scenario. Let's say a part coming off of a production line could be defective or non-defective. So there are only two possible outcomes here, which are mutually exclusive. And then let's say the part being defective is the success, then the part being non-defective is a failure. So any experiment which has two possible outcomes would be a Bernoulli trial. Okay, the light is on or off. There are two possible outcomes. So with this, these will be the characteristics of a Bernoulli trial. First of all, the trial results in one of the two mutually exclusive outcomes. So one or the other has to happen. The outcomes are exhaustive. That means these are the only possible outcomes, yes or no, success or failure. There is no third outcome that is possible. And the way we define the probabilities are the probability of success is the probability of S, which is defined as P, the lowercase p. And the probability of failure is defined as Q. And the total probability P plus Q is 1. Or in other way, Q is equal to 1 minus P. Okay, so that's the setup of a Bernoulli trial. Okay, now we can also, we need to define this as a discrete random variable, so we can't use success and failure. So we have to give a value to a discrete value to our random variable y. So we'll define our random variable y, which is a Bernoulli random variable in this case. It can take two possible outcomes, and we'll call these outcomes 1 and 0. So when we have a success, y is equal to 1. If we get a failure, then y is equal to 0. The probability of 1 is p, and the probability of 0 is q. Okay, so this is how we can write it. Y is equal to 1 if we have a success, and y is equal to 0 if we get a failure. Now, to understand the probability distribution of a random variable, we can use the probability of y will be equal to the probability of success p raised to y times q raised to 1 minus y. Okay, so what this is telling us that the probability of, let's say y is 0, in that case, whatever the probability of failure is, we use that as P, and the probability of success will be used as Q. We can also calculate the mean and variance for the Bernoulli random variable. The mean of a Bernoulli random variable is defined as mu, and it's simply equal to P, which is the probability of success. The variance is P times Q, which is probability of success times the probability of failure. And this is derived basically from the general definition from expected value of y and variance that we saw for a discrete random variable. So expected value of y is summation y times p of y. So value of the discrete variables, uh, the values the discrete variable can take times the probability. So a discrete variable can take the value of 1 or 0. The probability of 1 is p, probability of 0 is 1 minus p. But when you multiply it by 0, it's 0. So it's the mean is simply equal to p. Sigma squared, again, we know it's y squared times p of y minus mu squared. So again, if we plug in the values, our y can take value 0 and 1. The probability is again p and 1 minus p, and mu squared we just saw here is p. So when you subtract that, we get the probability, the variance is p times q for a Bernoulli trial. Okay, so Bernoulli trial, let's quickly review it. Bernoulli trial is the probability distribution of a Bernoulli random variable, which is an experiment where we can have two possible outcomes, 0 or 1, where 1 is the success, 0 is the failure, and the probability of y is given by p raised to y, q raised to 1 minus y. The mean is mu equal p, and then sigma squared, the variance is p times q. So Bernoulli trial is a very basic experiment. In real life situations, a lot of experiments are conducted as a series of Bernoulli trials. So imagine tossing a coin is a Bernoulli trial, and tossing a coin 10 times is a binomial experiment. Okay, so a lot of real life situations can be equated to this idea of the probability of tossing a coin. Let's say a coin is tossed 10 times, and we want to find the probability of getting heads 4 times. So that's the kind of situations or scenarios we can understand using the binomial distribution. So here is an example. Suppose that 30% of the private wells that provide drinking water to a metropolitan area contain impurity A. Then selecting a random sample of 10 wells and testing for impurity A would be similar to tossing an unbalanced coin, let's say, which has a probability of getting heads 0.30, same as the probability that the well has impurity A. So you can always look at what the experiment is, and if it follows these certain things, that each trial is a Bernoulli trial and it is a sequence or series of Bernoulli trials, it is a binomial experiment. Okay, another scenario, public opinion or consumer preference polls that elicit one or two responses, yes or no, approve or disapprove. So all these again are similar to the idea of tossing an unbalanced coin, and yes or no would be equivalent to saying heads or tails. Approve or disapprove, again heads or tails, with a probability which is p and 1 minus p. So these are the characteristics of a binomial random variable. The experiment consists of n identical Bernoulli trials. Then each trial here has two possible outcomes, a success and a failure. Okay, then the probability of success is p, probability of failure is q, and the sum of p and q is 1. Each trial is independent of each other. This is an important rule. That's what we saw in the previous chapter. If we have independent events occurring and we calculated the probability, now we are putting this together. We still have independent events, and we are trying to come up with a simplified formula to find the probability distribution. Okay, the binomial random variable will be y, and it will be what the variable uh, will be defined as the number of successes in n trials. Here is what the frequency distribution of looks like for a binomial random variable. So here are some examples. We have in each case we have a sample of 10. N is 10. That means there are 10 Bernoulli trials, and we have different values of p, the probability of success. So this is when probability of success is zero point 0.1. This is probability of success 0.3. Probability of success 0.5. It's almost similar to a normal distribution in this case. Here we have a probability of 0.7, and this is probability of 0.9. Okay, so these are the various shapes of the distribution for a binomial variable. Okay, now the probability distribution of the y can be given by this formula, and this is what we will use to find the probability of y successes in n trials. So let's say we flip the coin 10 times. What is the probability of 4 heads? Okay, so n is 10, y is 4. Y successes in n trials. So this gives a generalized formula for finding this probability without having to come up with a sample space every time, without having to count the number of trials separately, because the formula includes that. So if you look at this formula, this is what we're doing. Probability of y is n choose y. So this n choose y gives the possible number of combinations for y successes. Okay, so imagine this. We have 10 coins and we are trying to figure out the probability that we get 4 heads. Okay, so these 4 heads could occur in any sequence. We could have the second as heads, third place as third coin as heads, and then 6th and 10th, or 1 and 2 and 3 and 4, or all the combinations possible. So this formula gives us those possible combinations. So it's n factorial divided by y factorial times n minus 1 y factorial. P raised to y. So this is how we expand and choose y. Then p raised to y and q raised to n minus y. And the y can take values from 0 all the way to n. So y probability of 0 means 0 successes. Probability of n would mean that we have n successes. So if you flip 10 coins and you want to see the probability of getting 10 heads on all the 10 coins. So that's how we can use this formula now. So once we identify our experiment with a specific distribution, then we can directly use the formula to find the probabilities. And that's what we are trying to do here. Based on the properties of the experiment, we want to come up with the probability distributions. Okay, we can also find the mean and variance now for a binomial random variable. Mean is given by mu, which is equal to n times p. Okay, so n is the number of trials times the probability of success, and sigma squared is n times p times q. Again, we don't have to prove these every single time. We are, as long as we have identified our experiment as a binomial experiment, we can use the probability distribution, the mean, and the standard deviation formulas directly. Okay, so here is a look at how we are deriving the binomial experiment formula. So each trial is a Bernoulli trial. So let's say there are n Bernoulli trials. So let's say these are n trials. In the first trial, we get a success. Second is failure, success, success, so on and so forth. So we count the number of successes and the number of failures, and then all the possible combinations for the number of successes and the failures. Okay, so let's put this together. So let's say the first set is the number of successes, and this is the number of failures. Number of successes have a probability of p. These failures have a probability of 1 minus p. So p, let's say these are y successes, so there will be n minus y failures. So p raised to y and q raised to n minus y. So p is the probability of success, q is the probability of failure. Okay, and this gives us the possible combinations, number of combinations, and choose y. So n factorial divided by y factorial times n minus y factorial. Putting this together, we have our formula for finding the probability of y successes in n trials. Okay, now let's look at this example and then use the probability distribution and the mean and the variance formulas. Here's an example. Electrical engineers recognize that high neural current in computer power systems is a potential problem. A survey of computer power system load currents at US sites found that 10% of the sites had high neural to full load current ratios. If a random sample of 5 computer power systems is selected from a large number of sites in the country, what is the probability that exactly 3 will have high neural to full current load ratio, at least 3 will have high neural to full current ratio, or fewer than 3 will have a high neural to current ratio? We are trying to find the probabilities for these 3 cases: exactly 3, at least 3, and fewer than 3. Okay, so now let's see if this experiment is a binomial experiment. So there are 5 sites. So our n is 5. Each one is a Bernoulli trial because each trial will result in a success when a site has a high neural to full load current ratio, and it will be a failure if the system does not have a high ratio. Okay, so it's either success or failure. So 2 outcomes. So this is a Bernoulli trial. Each is independent of each other. Okay, so the outcome of one doesn't impact the outcome of the next trial. Now we have 5 such trials. So this is a binomial experiment with n equals 5, and probability of success is 10%. Okay, because 10% have high neural systems have high neural to full current ratio. So p is 0.1. Now we need to find the probability that exactly 3 sites have high ratio. Okay, so using the formula for our binomial distribution here, probability of 3, this is what we are trying to find. N is 5, y is 3, p is 0.1. So putting this in the formula, probability of 3 is 5 factorial divided by 3 factorial times 2 factorial. That's the n choose y part. 0.1 raised to 3 and 0.9, which is the probability of failure, raised to n minus y. So 5 minus 3 is 2. 0.0081 is the probability that exactly 3 sites have high ratio. Okay. Then the second part is, what is the probability that at least 3 sites have high ratio? So at least 3 would mean, in this case, there are the outcomes are 0, 1, 2, 3, 4, or 5. These are the values that our discrete variable can take. Probability of y greater than equal to 3 is 3, 4, or 5. So we add those 3 probabilities. So we have to find the probabilities individually by plugging into the formula. So 5 choose 3 for probability of 3. 5 choose 3 and 0.1 raised to 3, 0.9 squared. Probability of 4 will be 5 choose 4, 0.1 raised to 4, 0.9 raised to 1. And probability of 5 will be 5 choose 5, 0.1 raised to 5, 0.9 raised to 0. And the three values will be added together to give us the probability that y is greater than equal to 3, which is a very small probability, 0.00856. Okay, now let's see fewer than 3. Okay, fewer than 3 would be, the possible values would be 0, 1, or 2. Okay, now we could find the individual probabilities for 0, 1, and 2 and add them up. Or we could use the complementary rule here because we already have the probability of y greater than equal to 3. So for less than 3, we simply have to do 1 minus probability of y greater than equal to 3 from the previous part, and that gives us the probability as 0.99144, okay, which is pretty high. So the first three combined, 0, 1, and 2, those are the values which gives us the highest probabilities, and 3, 4, 5 have a lower probability. Okay, so that's all for today for the binomial distribution. There will be more examples coming up for the binomial distribution, and then we will discuss the Poisson distribution in the next lecture. Thanks for watching.